Imagine an intensive care unit where a patient in severe septic shock begins to spontaneously bleed. Symmetrical, pinpoint hemorrhages appear around the hair follicles on their legs, and blood pools painfully beneath the membranes of their bones. Standard coagulation labs, the prothrombin time, INR, and platelet counts, return a baffling picture. Despite the diffuse bleeding from almost every tissue, these markers remain perfectly normal. This creates a core medical paradox. The bleeding stems from a physical breakdown of the capillary walls themselves, rather than a failure in the blood's fluidic clotting cascade. The water and the plumbing logic are intact, but the biological pipes holding that water are turning to dust. This hemorrhaging represents a structural defect of the human extracellular matrix, a breakdown that is completely invisible to standard coagulation tests. The human vulnerability to this structural collapse traces back roughly 60 million years to a random genetic mutation in early primates living in a lush, fruit-rich canopy. This mutation permanently deactivated the gulo enzyme, stripping our ancestors of the ability to synthesize their own ascorbate from glucose. The molecule we stopped producing is L-ascorbic acid. Its molecular architecture centers on a specific active core, a planar, 5-membered enediol lactone ring. Because these primates were surrounded by a year-round buffet of fresh fruit, the diet masked the mutation. Over time, a standard metabolic byproduct became an obligate dietary requirement for human survival. We will decode ascorbate's architectural mechanism, map how the body hoards it, and examine the extreme pre-analytical protocols required to measure it in a clinical laboratory. Inside the human body, ascorbate functions as a highly targeted electron gun. Its primary task is to deliver electrons directly to specific metalloenzymes. Ascorbate targets prolyl and lysyl hydroxylase to build connective tissue. It docks in their catalytic pocket, firing an electron to lock the iron core in its active Fe2+ state. Normally, this creates a dangerous free radical, but ascorbate's resonance stabilization diffuses energy across its ring. Without this continuous supply of electrons, the iron core oxidizes and the enzymes lock up. Collagen chains can no longer form a rigid triple helix. Without this spark, uncross-linked collagen physically denatures at 37 degrees Celsius. The body's structural scaffolding literally melts at normal core body temperature. Knowing the risks of depletion, the body avoids leaving ascorbate to drift randomly in the blood. The free plasma represents only a tiny transport pool. The majority of the supply is sequestered in vital organs. Specialized active symporters, called SVCT2, act as high-power pumps. They siphon ascorbate from the bloodstream against steep concentration gradients to maintain pools in the brain and adrenal glands that are up to 100 times higher than the blood. During crises like septic shock, the immune system mounts a massive defense. To survive their own free radicals, white blood cells hijack glucose channels to absorb DHA, an oxidized vitamin C that mimics sugar. Once inside, they convert it into an active antioxidant shield. This massive immune hijacking can drain the entire plasma ascorbate pool in a matter of hours, triggering rapid multi-organ capillary leak syndrome. The body prioritizes this molecule across the lifespan. During pregnancy, the placenta upregulates its transporters to siphon maternal vascular supplies, ensuring the fetus has the structural reserves required for bone and tissue growth. In infants, this requirement is so high that thermal destruction of the vitamin causes Barlow's disease. Historically, infants fed exclusively on boiled cow's milk developed this specialized scurvy because high heat instantly shatters the delicate anediol ring. Attempting to bypass these limits with excessive oral supplements triggers a different set of mechanical failures, as the intestinal carriers have a hard physiological limit. When artificial doses exceed a few grams a day, the excess circulating ascorbate undergoes non-enzymatic cleavage into oxalate. This clears through the kidneys, where it binds to filtered calcium and precipitates into jagged, envelope-shaped calcium oxalate crystals. Humans exist in a narrow, high-stakes homeostatic balance. Too little results in structural dissolution, while artificial megadoses induce acute renal stone migration. Untangling the coagulation misdirection seen in septic patients requires a specific capillary leak multimarker check. The diagnostic pattern for scurvy is absolute, a critically low plasma ascorbate level paired with a completely normal prothrombin time and platelet count. This confirms a capillary basement membrane failure rather than a primary clotting disorder. Laboratory supervisors must also watch for chemical interference caused by the glucose reagent shift in severe diabetic patients. Because glucose and ascorbic acid are structurally similar, high urinary sugar can confuse automated dipstick tests, generating falsely elevated ascorbate or oxalate readings. Resolving these interferences requires strict diagnostic stewardship, ensuring specialized testing is ordered only for patients with documented malabsorption, severe malnutrition, or active capillary leaks. The most severe vulnerability in testing for vitamin C is the ex vivo auto-oxidation deletion trap. Atmospheric oxygen and warm temperatures rapidly destroy the NADL nutrix of a blood sample. If a tube sits unstabilized on a lab bench, the resulting decay generates a false low, potentially leading to a misdiagnosis of scurvy in healthy patients. Accurate measurement requires a strict cold chain protocol. The blood must be drawn on ice and centrifuged at 4 degrees Celsius within exactly 15 minutes. To freeze the oxidation kinetics, the plasma must be instantly mixed with metaphosphoric acid before being analyzed via high-performance liquid chromatography with electrochemical detection. A normal clotting profile never rules out a systemic bleeding disorder. Clinicians must recognize the structural necessity of ascorbate. L-ascorbic acid functions as the physical glue of human architecture, a volatile, system-critical post-translational catalyst. Maintaining our structural integrity depends on relentless biological hoarding, and for the modern laboratory, uncompromising analytical rigor to measure it.